Welcome to 6th lecture of video course on tribology. Topic of today's lecture is wear. So, W-E-A-R. It's not a clothing, it's a mechanism with which material deteriorates and loses its performance. In my view, wear is more important compared to friction. And a common definition of lubrication, which is generally given in a number of books, is that the lubrication is provided to reduce friction. I believe that it should be changed to the lubrication is provided to reduce the wear, because the effect on the wear is much more dominant compared to the friction. A general comparison, I can say that coefficient of friction from 1.00 can be reduced to 0.05 by a better design. This factor makes 20 times difference. However, if I do a good design, wear can be reduced by 100,000 times. That's much more dominating factor. I can choose a very good material pair or material pair with a solid lubricant. In that case, wear will reduce significantly, maybe 10⁵ times, which is very significant. So, to understand all this, let us start with a lecture wear and a definition. So, that undesirable removal of material from operating solid surface. In other words, wear is defined as undesirable removal of material from operating solid. I use the word undesirable, keeping in mind that there are two definitions. One is known as a zero wear, other one is a measurable wear. Zero wear means there is a wear, but that is not going to cost us much. In fact, it may increase the performance, it is a for betterment. So, that is not undesirable. However, measurable wear, where the undesirable wear occurs or undesirable removal of material occurs. Just to highlight that, let us see one small animation. You can see this, there are two material pair, orange and black. Orange is moving against the black, force is applied to push the block, but after some trials there is some asperity detachment from material 1 as well as some asperity detachment from material 2. This is zero wear. Here the detachment of asperities are smoothing the surfaces and filling the gaps or valleys, bringing overall roughness to negligible level. That is why when we refer this bathtub curve, we say there is a possibility of very high initial wear rate. It slowly comes down, it reaches to a steady state condition, and after certain duration it increases. So, we say that this is a infant mortality, that means in the childhood material is bound to wear out more. Then it will reach to normal life, where it has to show its own function. When that function life is over, then wear rate will increase. This is end of component life. So, we are more worried about this end part to estimate what will be the life of component, and we are more worried about this steady part, which is going to tell when component or is going to about to fail and what will be the maximum life which we can achieve from this. And this is a hypothetical curve, not necessary every curve, every wear curve will be like that. There is a possibility of continuous increase in a wear rate, it will never be in steady state condition. There is a possibility. That is why we need to understand wear mechanism properly. As I mentioned earlier, that this is a zero wear, which is not going to matter much to us. If component is improving performance, that will be always advisable, that will be always targeted. However, there is another kind of wear, which is a measurable wear. In this there are four figures shown A, B, C, D, and what we are trying to show a formation of pit which generally occurs if there is a load, there is a cyclic loading, and this cyclic loading is shown with these two arrows. That means there will be a mean value, there will be higher value than that, and there will be lower value than that. So, when the component or when the surface is subjected to this kind of cyclic loading, there is a possibility of formation of cracks within the surface. If there are too many cracks, they will agglomerate, they will make a one big crack, and maybe after certain duration, certain life cycles, this whole attachment will get detached, and this is what we know as the fracture mechanics. Component is getting or component is losing some material, a pit is formed on a surface, and that is why this name is given as a formation of pit. This is undesirable. If there are more and more number of pits, we know very well there will be some noise generation, there is a discontinuity in motion, and quite possible rolling motion is getting in sliding motion also. So, it is some sort of increase in the friction. We should avoid as far as possible this kind of failure, and that is a target to study the that is the main purpose to do a study on the wear and wear mechanisms. Let us see this roller surface. These are roller surfaces. We are able to find there are some scratches, some deformation of surface, or we can say it is losing some dimension, some tolerances. Quite possible that this scar may be the 20 to 50 micron, and 20 to 50 micron change in the dimension of tribopairs means a lot. It is going to change the performance from one domain to another domain, or we can say from full film lubrication to the mixed lubrication to the boundary lubrication, with the huge variation of coefficient of friction occurs. Just to elaborate that, we will take another example which we have shown also in the first lecture. This is a sliding bearing. This is a what we say crankshaft bearing. It has a middle groove for supply for oil, but we are able to see the scratches on the surface. These scratches may be 20 to 30 micron deeper, may occur maybe because of some particle or hard particles, sand particles, or some oxide which formed in the engine. Those particles will remove this surface, make some groove, or maybe display material. So, the roughness increases, and that change in dimension is going to change the clearance. What we say, the general bearing generally have a clearance of 0.1% of its radius, or is a radial clearance is 0.001 into radius. That is a very low. For 20 mm radius of the shaft, we are keeping 20 micron clearance. And if you are keeping 20 micron clearance and this kind of wear occurs, this is going to increase the wear by increase the clearance by 20 additional 20%. That means 40 micron clearance. Our performance will be very bad. Just to elaborate that, we can refer to this curve. You can say that when the clearance is equal to 0.001 R, then load carrying capacity is somewhat 625 Newton. As the clearance is increasing 2 times, then your load carrying capacity is coming down to the 150 Newton. So, from 625 Newton to 150 Newton, that is a substantial change in load carrying capacity. The component is bound to fail in that case. Was working in a hydrodynamic domain and suddenly started working in a boundary lubrication domain. That is a huge variation in friction, and performance will deteriorate, support will decrease, and it may cause whole failure of whole system. So, we need to understand that we need to avoid this kind of failure. That is why I have written here that the loss of dimension that changes the clearance value, and if this kind of loss of dimension happen, if there is an interference fit between the shaft and sleeve on top of that, which many times we use in bearing, inner race is mounted with a push fit on the shaft, And if this kind of wear occurs, a loss of dimension occurs, what will happen, even the inner wrist will try to run with a clearance fit, which is going to fail the bearing completely, and that should be avoided. So, let us come back to the wear definition. Once we hear now importance of wear topic, we will come to the again why the wear occurs. We said the removal of material from operating solid surface occurs by solids or by fluids. So, both the kind of wears are possible. Is a solid may cause the solid wear, or fluid may cause solid wear. When there is a wear by solid surface, then dependent parameter or parameter which are going to affect the performance will be load, velocity, environment and materials. If there is a good hardness of material or good compactness of material, then wear will be lesser. If environment is friendly, wear will be lesser. A larger velocity by and large will cause more wear except the hydrodynamic domain, and high load will cause high wear, except the few cases where the low load may cause some vibration and larger load will avoid that vibration. When we treat wear by a fluid topic, we say that it depends on the relative velocity and depends on the applied pressure or induced pressure. Here we do not use the word load, we use a more pressure because we know there will be uniform distribution, while in case of the load there is a more concentrated load also. So, that is why we use the word here the pressure, the dependence on the pressure. Of course, the remaining two parameters will be same, environment and material. A material is can sustain or can absorb the wear energy, then it will sustain its life, it will be longer life. Many times we say the harder material is preferred, but it is not always the case. Harder material may have a lower toughness, lower energy absorption, and many times it will fail much earlier stage compared to the softer material, which are which need to be studied properly. When we should choose a softer material, when we should choose a harder material, what is the reason behind that, we will be studying in this topic. Now, this block says wear increases, but before that I can add this: wear is never a catastrophic failure. We will never get immediate failure due to wear. Immediate failure will be because of some other reason. Wear is a gradual, it is more like our life. We gradually decay in our performance from 25 years to 50 years to 75 years, and that is a wear. Our bone joints are getting worn out, so we will not be able to run that much fast, we will not be able to do that much physical work. Same thing happens to the all machine. So, failure is a gradual, it does not happen immediately. If it is happening immediately, then there will be some other cause of failure, it will not be just wear, or in other words, wear may initiate other cause for spontaneous failure, but wear itself will not be allowed or will not be able to cause the immediate failure of the component, but it causes some other problems. So, if wear increases the power losses, the friction losses will increase, there is a wear of the surface. And here I am talking about the measurable wear, I am not talking about the zero wear, or we are not talking about the initial wear, where the asperities are getting damaged or deformed or displaced for the betterment. If that kind of wear occurs, that is good for us, good for our machine. Second is the oil consumption. If there is a wear is more, than oil consumption will increase. There is a possibility of leakage, excessive leakage from the interface, and that will start consuming more and more lubricant, or we need to supply more and more lubricant. And finally, we say that if there is a more wear, there is a naturally possibility of replacing or replacing that component with a newer component. So, in short, wear does not cause spontaneous failure, but surely it is going to cost power, is going to cost oil, is going to cost replacement. So, indirectly it is costing us. If we are able to avoid it, there will be economic benefits to us, and we want those economic benefits. When I talk about the wear mechanism, it's difficult to talk about the wear mechanisms. There are too many wear mechanisms available. People have given theories and theories on wear mechanism. As far as my knowledge is concerned, there are more than 35 mechanisms. When we start, there will be, we can say there is a abrasive wear, there is a adhesive wear, and there is a cavitation wear, there is corrosion wear, erosive wear, fatigue wear, and phatic wear. Now, each topic can be further subdivided in number of categories. Let us say abrasive wear, we are talking about the polishing. Polishing is a good phenomena to give a final finish to surface, but many times it is not advisable to us. Scoring, the scratching, grinding, gouging, they are subdivisions of abrasive wear. Coming to adhesive wear itself, the magnitude is changing, whether there is a low magnitude adhesion, medium level adhesion, high level adhesion, whether there is a cold or whether hot. The number of divisions are there. Basically, basic mechanism will be same, but magnitude will change. That is why the relations will change. Dependence on the different parameters will change. When we talk about the cavitation, basically we are talking about the solid versus liquid. It is something like some bubbles are getting burst, and because of the bursting of the bubble, there will be excessive pressure, which will be directly impinging liquid with a high velocity on the surface, and that will cause some failure, or that will be known as a cavitation failure. Similarly, there is a corrosion wear. There is a combination. Corrosion happens because of the chemical action. It increases the porosity of the surface, and if there is a mechanical action on that, naturally there will be easy wear out of that surface. Loose particle, or we say that porous layer will be easily removed by mechanical action. So, there is a combination chemical and mechanical, and by and large we say that wear is a mechanical. So, that is why I have written here that it is having chemical nature. That means, initiation happen because of the chemical action, and finally, result or removal of material happens because of the mechanical action. There is another kind of wear which we know, the erosive wear. It happens again because of the liquid or the high velocity liquid or high velocity particles also. Particles, they are generally more common to cause erosive wear. Maybe typical example is fly ash. If it is a high velocity fly ash impinges directly on the surfaces, it will cause excessive wear. Another wear is a fatigue wear, and one category of the fatigue wear itself is a delamination. It can be a surface wear or it can be a subsurface wear. So, there is a division possibility, or we can classify accordingly, and there will be different theories to treat this topic. And finally, is the phatic wear. I take a very good example. You say that do nothing, no movement between two surfaces, but still there is a possibility of wear. If you get a chance to open any nut and bolt connection anytime, open it and you will find some sort of the black powder or red color powder comes out of those nut and bolt connection. I am talking about the ferrous material. If the nut and bolt connection are made of the ferrous material, whenever you open, you will find some particles, some black powder, some red color powder comes out of that, and that is a phatic wear. We are talking about micro motions which are induced with the vibration, even though there is no relative velocity, but there is a micro motion, there is a micro slip phenomena happening. It will again and again knock the surface and will cause some failure, some removal of material, and even the particles which are getting removed from the surface, those will increase this kind of wear. So, we should generally we avoid it if we understand all these mechanisms. I have given one of the example of abrasive wear, what we are calling the polishing wear. I took this example because most of the time we say that polishing is favorable phenomena, it should be done, and if it is done, what are the problems? You can see this is the first figure. In this case, is the liner figure, is the engine liner. Your polishing happened. If this kind of the polishing happen, what will be result? If the surface is textured to retain the lubricant, the texture will be removed, and if that texture is getting removed, we are losing performance. If I say some sort of diamond shape given to the liner to retain the lubricant, to keep those diamond shape as a storage for a storage purpose, and if those diamond shapes are getting polished, naturally that performance will come down. Whatever we optimize the surface to retain the lubricant properly, those will be removed. Some other performance will come because the polishing is going to generate some other surface, some other group parameters, which may not be optimized or optimal parameters. Naturally, because of that, some problem will come. I can take a very good example about the carbon graphite and stainless steel. We are able to see these black marks on stainless steel surface. These marks have come directly from carbon powder, and here it has been done intentionally. What we are saying that let carbon graphite transfer its layer on the stainless steel, because adhesion between stainless steel and carbon graphite is higher compared to cohesion between graphite and graphite. So, a weak interface will be made between graphite and graphite surface, but good adhesion will be made between the carbon graphite and stainless steel. Once this layer is getting deposited, carbon graphite layer is getting deposited on the stainless steel surface, we are going to reduce coefficient of friction and subsequent wear. In other words, initially there will be high wear because of the transformation of the layer from carbon graphite to stainless steel, and subsequent to that wear rate will come down, friction will be reduced. We talk maybe say the coefficient of friction initially around 0.3, 0.4, and subsequent to transfer of this layer, coefficient of friction may be reduced to the 0.2. So, almost 50% benefit is on that, and we desire it. Now, if somebody by mistake thinks, oh, this surface is getting dirty, oh, some black marks are there, I want to polish at every new operation and get good performance, then he will be mistaken. This layer have been deposited intentionally. It has the basic physics behind that, and if somebody without understanding it tries to remove, no, this is dirty surface, it should be cleaned before assembly, then he will cause unnecessary failure of the component, unnecessary wear of a surface, and higher power loss. So, that is a polishing wear, right. However, wear itself is a complete subject, and we require maybe say 40 to 45 lecture itself on the wear. We do not have that much time. So, what we will do, we will try to cover this wear in 4 lectures, and basically we will cover abrasive wear, adhesive wear, corrosive wear, erosive wear, fatigue, and phatic wear. These important topics will be covered. Remaining topic which can be derived from this basic mechanism remains same, like a number of subdivision under abrasive wear can be treated in similar manner, only the coefficients will vary, parameters will vary to some extent. Now, if we come to the abrasive wear, we see there are basically 4 mechanisms which will give physics of the abrasive wear, and depends if the material is ductile or brittle, mechanism will change. Let us take an example of micro cutting. We are talking here the sharp particle hard asperities. If there are no sharp particles, it will shift to the micro fatigue. So, if the more sharpness, it will cause micro cutting. If the lesser sharpness, more roundness, then it will cause a micro fatigue. If the material is brittle, it will cause micro fracture or directly removal of the grains. So, depends on the whether material is ductile or brittle, physics will slightly change, relation will slightly change. And whenever the particles or material is getting removed from the surface, we will call this as a wear debris. If the material is getting displaced, maybe initially due to fatigue or some sort of flowing effect, we will not be able to gain or wear debris, it will be just a surfacing of the surface. Wear debris is a loose particle, and those loose particle may further increase or decrease wear rate, depends on the operating parameters. Now, this is a typical example for micro fatigue. We say that two surfaces are moving relatively, maybe top surface can move right hand side, lower surface can move left hand side. That means there is a relative velocity. Now, the situation may be anything. Absolute motion of top surface as moving to the right side, and the bottom surface is stationary. Still there is a relative motion, or top surface is stationary, bottom surface is moving against the top surface, then again there is a relative motion. What will happen because of relative motion? And the asperities of the blunt, they are not very sharp, they are not conical, maybe we can say that these asperities are spherical in nature. So, it is going to cause again and again stress of the surface, stress is induced, and it turn out to be cyclic loading of the asperities, again and again load and unload, load and unload. That will cause some sort of crack formation in this asperity itself, or maybe the beneath the spirit also. So, after certain duration, so certain cycles, this will get fractured, and due to fracture there will be new surface generation, which may be smoother or worse than earlier surface, depend on the rate of the loading which we are applying. If the rate of loading is very, very high, there are more chances that this surface will make a big pit in the surface itself, which should be avoided. So, this is what we say the micro fatigue, generally caused by spherical cavities. Micro cutting is caused mostly by conical cavities, and there will be always a mixture of these two. Similarly, macro fracture, it is it generally occurred in ceramic material, more brittle materials, where particle cohesion is not much higher, and they are made of with some sort of cohesion which may not be having very high value. And sometimes they are weak, having a weak grain boundaries, and they are not treated properly, then ceramic materials will deteriorate using due to the wear phenomena, where the whole grain will come out or get separated from the parent surface. This abrasive wear is having a very common mechanism with erosive wear and cavitation wear. Only the difference is that in abrasive wear we are talking about the two solids, or we are talking about the particle not with the impingement, not with the impact, but sliding come rolling motion. So, the wear abrasive wear is generally solid versus solid, but particles are not coming with a high velocity, while in erosive wear we are talking about the particles which are attacking the surface with a relatively high velocity. When we talk about the cavitation, we are talking about the liquid which is making bubbles, or bubbles are induced because of one process or one way or another way, and they are getting burst, releasing the high pressure, and due to that pressure surface is getting damaged. Now, further we will come to the wear. We say that basic modes of the wear, abrasive wear, can be further classified based on whether they are asperity versus asperity or particle versus asperities. If asperities versus asperity interaction occurs, we call as a two body abrasion. Where the particle versus asperity interaction happens, we call a third body or a three body abrasion, assuming particle loose particle as a third body. We already have a two surfaces, soft surface and a harder surface, and there will be some particle in between. Naturally, a question arises: is a two body abrasion bad or three body abrasion is bad? Which should be preferred? Experiments show that two body abrasion is causing slightly higher wear rate compared to three body abrasion. And then slightly, maybe again a subjective, many times we have observed that three body abrasion cause only 10% damage compared to two body abrasion. So, number of parameters are going to affect particle shape, particle size, or everything will matter when we talk about the abrasive wear by three body abrasion phenomena or mechanism. Let us start with the two body abrasion. We will try to develop some quantified quantification of the relation and how this wear can be reduced. When we have model, mathematical model, we can play with the parameters. So, what is written here? The example is given as a polishing by emery paper. You must have seen a number of manufacturing operations where the final finish is given by polishing paper, or we call it emery paper, which has a grid, which has abrasive particles, and they are manufacturing the surface or giving final finish to that, but that is a desirable. Here what we are talking about is undesirable, which should be avoided. So, in this case we can take a conical asperity where the half cone angle is alpha, and when the due to depth, and the depth is occurring at the radius a, is a conical, right. So, wherever the interaction happens, there will be a circular cross section, and circular cross section will be having some radius. So, we are talking about that radius as a, and this will occur whenever we load harder component against the softer component. Under load, this asperities will penetrate softer material to balance the load, to bring in the equilibrium, and if we provide a sliding to the surface, then there is a possibility of dragging this asperity against the soft material. There are two options. Material gives its path, soft material gives a path to the harder asperity, displays the material to the other side. Our possibility is that completely remove that material from the surface. If harder asperity is coming, material is simply getting detached from the surface. Both the possibilities are possible, both the possibilities are there. Sometimes we get more plowing effect, sometimes we get more cutting effect, but there will be a balance of these two, and sometimes there will be only elastic deformation, there will not be any plastic deformation if the applied load is much lower. In that case, we are not going to lose anything, it is only deformation of the material under elastic limit and regaining that shape. However, to develop the relation, we are assuming whatever the material is getting transferred, or whenever there is a sliding of the harder asperities against the softer material, we are assuming that whole material is getting detached, cut from the parent or soft material. That will give us very high value of wear. Then we can introduce some coefficient, some probability. The probability may be 10⁻³ 10⁻⁴ 10⁻⁵. That can be determined by experimental results, because we cannot really get this overall good results if there are too many asperities. All asperities have different heights, different radius, different shapes. So, we assume, let us take one asperity and assume the same shape of all asperities causing similar phenomena, and there is equal distribution of load. All asperities are sustaining same load, which is totally hypothetical, not even close to the realistic value, but we need, then in that case we need to bring a very good statistical model, which will be slightly complicated, we will not be able to judge. So, that is why what we do, we take a simple example, develop the equation, find out some unknown parameter, do experiments and figure out what is that parameter. that parameter may be a constant or non-dimensional, that shows some probability of the success. If the probability is very high, wear rate will be very high because we are taking an extreme case. If probability is lower, that means wear rate will be lower. Just to understand that, we will come back to the slide. We say that normal load causes penetration, which has been explained, and it is causing a plastic deformation. In actual, there will be elastic deformation also. We are assuming 100% plastic deformation, and there will be micro cutting and micro flowing, but we are assuming all micro cutting, detachment of surface, that asperities or that material completely from the surface. And in this case, we assume the radius is a, that means diameter will be 2a. As is a conical shape, area here is a pi a square, but I will take half of that and multiply with hardness, because our assumption is the plastic deformation. Material is undergoing plastic deformation, and easiest way for that is you multiply with the hardness. If it is undergoing elastic limit, then I will be multiplying it with the yield strength or proportional limit. So, we say that one asperating harder asperity when penetrate into the softer surface, softer material, contact radius at the surface will be a, and it will be circular cross section. So, pi a square is area, and point which is touching is a pointed. So, there will be area will be 0, average area will turn out to be 50% of pi a square. We are multiplying with the hardness to find out load sustained by one asperity, and we need to find out the volume, because we are talking about we are discussing about the wear rate. We want to find out how much wear will occur on that surface. So, in that case we need to find out what is the swept volume, how much volume has been displaced. That can be figured out from the radius, distance which is traveled L, and depth of the penetration. So, depth of penetration is x, radius of the cone is a, and radius of a cone at the contact surface is a, and total distance travelled by this asperity is L. We can express the depth of the penetration in terms of cone angle, that will turn out to be a by 10 alpha. Here alpha is half cone angle. Rearrange this equation by substituting W n instead of a square. What we get is W n asperity load on one asperity or load sustained by one asperity, 0.5 the 50%, hardness pi 10 alpha into distance travelled by this asperity. Now, I can do integration if there is a continuous phenomenon, but asperities are generally discontinuous. So, we assume some asperities may be number n. We do not know whether n is 1000, 10,000, 100, it can be anything. What we need to do is summation. So, asperities 1 to n, and load may be different in every case. So, summation will turn out to be overall load, overall normal load which is applied. Distance can be easily calculated, it can be easily measured, and 10 alpha we do not know, that is a statistical parameter. For few asperities it will be 1 maybe 10 degree, maybe few asperities it will be 80 degree, few asperities it will be 50 degree. So, still we are assuming there is a statistical parameter, we are not taking any decision. However, the hardness of the surface is measurable. So, L is measurable, H is measurable, W is measurable or is which is applied. So, we arrange this equation something like that, L, W and H, and if we are trying to find out volume per unit length, that will be V by L, assuming that is equal to Q. Expression turn out to be 2 by pi 10 alpha W by H. This measurable, and this is a, we do not know, we have taken some approximation. I can treat this as a one constant, and I can figure out when I do the number of experiments on that, what will be the value of this constant. So, we say Q is equal to K, a constant need to be determined by doing number of experiments, W applied load and hardness of the surface. So, we need to find out this K, which generally depends number of parameters, and by and large it depends on the chemical nature of the material and environment. If you change environment, value of K will change. If you change a material, value of K will change. Other than this, there is affecting parameters W, which is proportional, that means increase the load, Q will increase the hardness, Q will decrease, but it is not always the case. In case of the ceramic material, we need to find out whether the material has that much energy absorption capabilities. If energy absorption capabilities is not there, even increasing hardness is not going to help us, because wear phenomena will change. It will cause some more fracture of the surface compared to abrasion. We have couple of curves of experimental results. This shows the dependence of hardness, but this slide shows that it is not only the hardness, it is the ratio of hardness which is important. What is the hardness ratio of harder to softer surface? If hardness is very high, let us take a 10. Hardness of a hard surface versus or compared to the softer surface is very high, then wear rate will be very high. However, if the this hardness is equal to 1, still there will be wear rate. It is nothing like I keep 60 HRC hardness of one surface and 60 HRC of hardness of other surface, and I try to slide one surface over other surface, there will not be wear. Surely there will be wear. Even though there is a equal hardness, there will be some wear. Asperities, however, asperities can be treated as a cantilever and their height is different. If the height is too high, it will act as a very weak element in surface. It will simply rupture from the surface. So, even though for the equal hardness, there will be wear rate, and that is indicated here. Even the wear rate is this ratio is equal to 1, still there is a hardness something. Now, if this hardness ratio decreases, that means wear rate will come down, but of the other surface, it will not be for the one surface. There is another possibility of a material combination. We say that whether material is homogeneous or heterogeneous. If the material is homogeneous, wear rate will be lower. There is a more closeness of the particles, and displacing those particles will be slightly difficult. There will be more resistance on that, but material is a heterogeneous, then it can absorb more energy, but it will cause more wear. It may be plugged out easily, it will be simply it can be removed easily. So, depends on the homogeneity or heterogeneity of the material, behavior or wear behavior will be different. That was a 2 body abrasion. Now, we can think about the 3 body abrasion also. As I mentioned initially, that 2 body abrasion is more harmful compared to 3 body abrasion, and this slide is giving reason for that. It says when particle is detached from the surface, it does not have any rigidity. If you allow movement of the particle, there is a possibility of sliding as well as rolling, and rolling, because it has a lesser coefficient of friction, rolling will be more dominant. For the same force, rolling will be more dominant compared to sliding, if the shape is proper. Of course, if the shape is very irregular and one dimensional shape, then sliding will be more. But if the particle has more like a spherical shape, if you push it, there will be more and more rolling. So, what we can say, for loose particle, even though the hardness is very high, for loose particle there will be overall lesser sliding distance, because there is more rolling distance, and if that is the case, wear rate will be reduced. It will be much lesser. most of the energy is being absorbed in the rolling action. That is why if I compare constant K with a 2 body abrasion and 3 body abrasion, or maybe a comparison between 3 body and 2 body, what we are gaining, this is wear rate, it may be say is a non-dimensional number, wear rate may be say 5 into 10 raised to minus 3. This is just an assumption. I am not talking that wear rate will be like this always, depends on the material combination. But if the wear rate is something like a 5 into 10 raised to minus 3 for one triber pair, if I come to the 3 body abrasion, it will be reduced by 10 times. It will be 5 into 10 raised to minus 4. Again, it is an approximation, no absolute value, not 100%, but chances are there wear rate will be decreased significantly, maybe say 1 order of magnitude. Reason being, particles are rolling more, causing lesser damage to the surface. But again, that rolling ratio will depend on the shape of the particle. If the particle is spherical, is having irregular shape or more like a diamond shape, which will cause more and more scratching or lesser scratching. Depends on the shape of the particle, we can find out that wear rate is much lower or higher side. These particles, the third body, generally occurs because of oxidation and a detachment of oxide layer from the surface, or some other wear phenomena, maybe because of the adhesion, junction formation occurs, and then there is a that fragment of the surface or removal of the adhesive pair, adhesive junction that may be generated as wear debris, that will cause abrasion, or means the adhesion is leading to the abrasion, 3 body abrasion. Interesting thing is that if we know clearance between two surfaces is a larger than particle size, then this third body abrasion will not cause much damage. In other words, we know the particle size which is getting generated between the two surfaces and between the one pair, then we should keep clearance in such a manner particles which is coming or which is interposed between the two surfaces is not going to cause much failure. To find what is the effect, easiest one is finding the roundness factor. Roundness factor f is generally given as a ratio of 4 pi into area of cross sectional area of the body divided by perimeter square. If I think about the spherical shape, the cross section is a pi r square, r is a radius. So, this will turn out to be 4 pi square r square, and we know the perimeter of circle is 2 pi r. So, it will square will be 4 pi r square. So, overall roundness factor will turn out to be 1. In other words, if the roundness parameter is equal to 1, that will cause a lesser or this a least wear 3 body abrasion compared to irregular surface, and that is the reason many times we use particles for the lubrication, and particle shape is kept as a spherical shape, which is not going to cause any failure, which is not going to cause abrasion of the surface. That will be always advisable. Choose particle shape in such a manner which causes a lesser abrasion. If we are using particles as material to lubricate the surface, I can take a very simple example to demonstrate practical particle size, but we say that MR fluid, magnetorheological fluid, where the particles are used or iron particles are used, may be having good hardness. Generally, we try to keep this particle as a sphere. Just to give more information of MR fluid or magnetorheological fluid, you can assume there is a one cell filled with a liquid, and these are the some solid particles in that, and this liquid works with the magnetic field. That means, if I apply a magnetic field, this field is shown in by H in direction. If I apply this magnetic field, this iron particle will chain up Again, this is the ideal one. Not necessary particles will always chain up. They can make clusters. They can make a 3-4 rows, 3-4 columns, not equal in size. It's something like a particle may come attached this point, get attached to this point, and next particle will get attached to this point. However, between two columns there will be repulsion, so they will get separated. But filling of this gap is possible. That means, not necessarily it will be always a chain. There is a possibility of the cluster formation, which we have observed in number of times in a lab. It is cluster formation compared to chain formation, and this cluster formation increases the strength of amorph fluid, which gets solidified. However, if now if we apply a tangential motion, if you apply some shear rate, there is a possibility of bending of this particle chain, but this is as a velocity is applied, this particle should abrupt the contacting surface. If we do not keep spherical shape, a particle do not have a spherical shape, then there is a possibility of scratching of confining surfaces where the amorph fluid is confined. Those surface will get damaged, because iron is a relatively harder material, and if you are trying to keep use seals or rubber seals to stop leakage of this amorph fluids, relative velocity will try to damage that rubber. Rubber is very soft. So, we are keeping soft material, but against this iron particle, but we are keeping a spherical shape. We are trying to think about all maybe say 90 to 95% energy is used for the rolling purpose. It is not utilized to abrupt the surface. So, if we are able to keep that, we can make very good mechanism, or we say the liquid or smart liquid, which shows the good results. I have one slide or image which says that 20 micron is the size, this size, and these are number of particles in MR suspension. We know very well that this particle are much smaller than 20 micron, and if we see the particle distribution, what we get. So, 0 to 1 micron, around 841 micron particles in that in one patch, 1 to 2 micron around 736, 2 to 3 micron is 76, and in 3 to 4 is only 6 particles. Beyond this size, there is no particle. If I take a mean value, you say that mean value turn out to be 1.10 micron, minimum and maximum is 3.93. There is some standard deviation of particles. So, here we are keeping two things, one is a spherical particle and as well as the particle size smaller. Lesser the particle size, lesser will be the abrasion. As the clearance is more, particle size is lesser, then it will simply roll, it will not get obstructed anywhere, and abrasion will be low. However, if particle size is increased and the clearance space between which the particle has to move is reduced. Think our clearance is only the 20 micron and I am getting a particle size of 25 micron. Naturally, it will not be able to roll easily. It will try to damage the surface, either increase the clearance or remove its asperities one way or another way, or corners, remove its edges and make shape in such a manner which can easily pass from 20 micron gap. So, there is a possibility of these two, and we can reduce abrasion by choosing proper size of the particle, choosing the shape or making the shape of particle. Even in many times, if we are not able to make complete round shape, particle will turn out to be round, it will increase its roundness factor during the wear process itself. Sharp edges will be terminated or will be smoothened or will be rounded, it will give us good results. So, with this I am trying to close the lecture on abrasion wear. Next lecture will be more emphasis given on adhesion wear, which is very important We know that adhesive wear is not as harmful as abrasion wear, and most of the components are failing because of abrasion, but adhesive wear can give or can lead to the abrasion wear. It can give some particles or generate debris which causes the failure due to the abrasion. So, they are dependent on each other. Thank you for your attention.